In chapter 3, module 1, we have explained the method of successive approximations to solve a Fredholm integral equation of second kind with continuous kernel and forcing term. In this module, that is module 2 of chapter 3, we shall illustrate the method of successive approximations and we shall consider few examples to solve Fredholm integral equations of second kind. Consider the Fredholm integral equation of second kind of the form given by equation 3.15. Here kxt and fx, these functions are continuous. We have already obtained the solution of equation 3.15 by the method of successive approximations in previous module, and by this method we have seen that the Newman series solution of this integral equation exists provided the parameter lambda satisfies the condition given by equation 3.16, that is mod lambda into capital M into b minus a, it should be less than 1 in order that the Neumann series solution exists. Here capital M is the supremum of the function mod kxt, x and t both belongs to closed interval AB. Now, the restriction on lambda as given by equation 3.16, for which the Neumann series solution converges absolutely and uniformly as proved in previous module of chapter 3, that is chapter 3 module 1, is just a sufficient condition. There are examples of integral equations of the form given by equation 3.15 for which the Neumann series converges for a weaker restriction on lambda. Now we shall illustrate this fact by considering the following example. In example 1, we had to obtain the Neumann series solution of the integral equation given by 3.17. Now, if I compare this integral equation with the integral equation given by 3.15, then in this case the forcing function fx and the kernel kxt are given by kxt equal to xt, a is equal to 0, b is equal to 1, and phi superscript not x, that is equal to fx, and that is equal to 1 in this case. With this information, we now calculate phi superscript 1x, and that is given by integral 0 to 1 kxt phi superscript 0t dt. And we know that phi superscript 0t is equal to fx, and that is equal to 1. So, substituting that value, we get phi superscript 1x is equal to x by 2. Next, we calculate phi superscript 2x, and that is given by integral 0 to 1 kxt phi superscript 1t dt, and if I substitute the value of phi superscript 1t, then after simplification I get the value of phi superscript 2x equal to 1/3 into x by 2. Similarly, I calculate phi superscript 3x, and that is given by integral 0 to 1 kxt phi superscript 2t dt. In a similar manner, I substitute the value of phi superscript 2t here to simplify the integral to obtain the value of phi superscript 3x as 1 by 3 square into x by 2. If I continue this process, I obtain phi superscript nx, and that is equal to integral 0 to 1 kxt phi superscript n minus 1 t dt. Similarly, substituting phi n superscript n minus 1 t, we obtain the value of phi superscript nx as 1 by 3 to the power n minus 1 into x by 2. Thus, calculating all the phi superscript nx, we find the Neumann series solution of the given integral equation as phi x equal to summation n equal to 0 to infinity lambda to the power n into phi superscript n x. Substituting the value of phi superscript n x, we obtain phi x in terms of a series given by phi x equal to 1 plus lambda x by 2 summation n equal to 1 lambda by 3 whole to the power n minus 1. Now this series will converge if mod lambda by 3 is less than 1, and this sum of this series is given by 1 by 1 minus lambda by 3. So we get phi x as 1 plus 3 lambda x divided by 2 into 3 minus lambda after simplification. And the solution is obtained for lambda satisfying the condition mod lambda less than 3 as given by equation 3.19. Now, we observe that the condition 3.16, that means mod lambda into capital M into B minus A less than 1, if I calculate the value of lambda from this condition, we get that mod lambda should be less than 1. This condition is much more stronger than the restriction on lambda as given by equation 3.19, that is mod lambda is less than 3. So, this shows that the condition given by 3.16 is a sufficient condition. Thus, through this example, we have seen that the condition on lambda as appeared in the method of successive approximation is just a sufficient condition. We shall now consider few more examples. Now we consider example 2. Apply the method of successive approximations to find the nth approximation to the solution of the Fredholm integral equation given by phi x equal to x plus integral 0 to half phi t dt as given by equation 3.20, and hence we are to find its exact solution. Now, if I compare this equation with the given integral equation, we see that in this case the forcing function is equal to x, that is fx is equal to x, the kernel is equal to 1 and a is equal to 0 and b is equal to half, where a and b are the lower and upper limit of integration, and in this case the parameter lambda is equal to 1. Now we assume that the 0th approximation to phi x, that is phi naught x, is equal to fx, that is equal to x. Now if I substitute phi x equal to phi naught x equal to x in the integral 3.20, that is in place of phi t, here I substitute phi naught x to obtain the first approximation phi 1 x to phi x as phi 1 x equal to x plus integral 0 to half t dt, and that gives x plus 1 by 8. So we have obtained the first approximation of the solution of given integral equation. Again, I substitute in place of phi t in the integral on the right hand side of equation 20, phi 1 t, that is the first approximation obtained. Then we obtain the second approximation phi 2x of phi x, the solution of the integral equation, as phi 2x equal to x plus integral 0 to half t plus 1 by 8 dt. Simplifying, we obtain the second approximation phi 2x equal to x plus 2 square minus 1 by 2 to the power 4. Similarly, we can find the third and fourth approximations phi 3x and phi 4x to phi x as phi 3x equal to x plus integral 0 to half phi 2t dt. If I substitute phi 2t dt, then we get phi 3x after simplification as x plus 7 by 32, which can again be written as x plus 2 cube minus 1 by 2 to the power 5. Similarly, phi 4x, that is the fourth approximation to phi x, is given by x plus integral 0 to half phi 3 t dt. If I substitute phi 3 t in this integral, then after simplification I obtain the fourth approximation phi 4x as x plus 2 to the power 4 minus 1 by 2 to the power 6. If I continue this, then the nth approximation phi nx of phi x is obtained as phi nx equal to x plus integral 0 to half phi n minus 1 t dt, which can be obtained as, after simplification, phi nx equal to x plus 2 to the power n minus 1 divided by 2 to the power n plus 2, which is given by x plus 1/4 minus 1 by 2 to the power n plus 2. Now, this term 1 by 2 to the power n plus 2 tends to 0 as n tends to infinity, so that the nth approximation phi nx tends to x plus 1 by 4, and this gives the exact solution phi x of the given integral equation as n tend to infinity by the method of successive approximation. So, by the method of successive approximation, we have obtained the exact solution of this integral equation. Next, we consider third example. Find the Neumann series solution of the integral equation phi x equal to 1 plus lambda integral 0 to pi by 2 phi t cos x dt as given by equation 3.21. Here, if you compare this equation 3.21 with the Fredholm integral equation, then we find that the forcing function fx is equal to 1, the kernel kxt is equal to cos x, the lower limit of integration a is equal to 0, and the upper limit of integration b is equal to pi by 2. So, with this information, we are to find the Neumann series solution of integral equation 3.21. Now, we defined phi superscript naught x, that is equal to fx, and that is equal to 1 by the given problem, and phi superscript nx is equal to the integral 0 to pi by 2 kxt phi superscript n minus 1 t dt, n runs from 1 to etc. as given by equation 3.22. So that we obtain phi 1x, that means phi superscript 1x, as integral 0 to pi by 2 kxt phi superscript naught t dt. Here kxt is cos x and phi superscript naught x, as assumed by us, it is equal to fx, and that is given by 1. So, if I substitute all these, then I get phi superscript 1x equal to pi by 2 cos x. In a similar manner, we can find phi superscript 2x equal to integral 0 to pi by 2 kxt phi superscript 1 t dt. So, if I substitute kxt as cos x and phi superscript 1t equal to pi by 2 cos t, then after performing the integration I obtain phi superscript 2x as pi by 2 cos x. Note here that phi superscript 1x we have obtained equal to pi by 2x. Also phi superscript 2x we have obtained as pi by 2 cos x. Similarly, phi 3 superscript 3x, phi superscript 4x, etc., that is phi superscript jx, can similarly be obtained as pi by 2 cos x, as given by equation 3.23. Now, the Neumann series solution is given by phi x equal to summation n equal to 0 to infinity lambda to the power n phi superscript nx. Now phi superscript nx we have obtained for all n equal to pi by 2 cos x. So if I substitute this value, so I get the Neumann series solution as phi x equal to pi by 2 cos x summation n equal to 0 to infinity lambda to the power n. Now, the series on the right hand side, that is summation n equal to 0 to infinity lambda to the power n, this converges for mod lambda less than 1, and the sum is equal to 1 by 1 minus lambda. So, the solution of the given integral equation, that is the Neumann series solution of the given integral equation, is given by phi x equal to pi by 2 cos x divided by 1 minus lambda, and this solution is valid for mod lambda less than 1. Next, we consider another example, that is example 4. Here we have to obtain the Neumann series solution for the integral equation phi x equal to 1 plus lambda into integral 0 to 1 e to the power x minus t phi t dt, as given by equation 3.24. Here the forcing function fx is equal to 1, the kernel kxt equal to e to the power x minus t, the lower limit of integration a is equal to 0, and the upper limit of integration b equal to 1. To obtain the Neumann series solution of this integral equation, we define phi superscript naught x equal to fx, and that is equal to 1, and phi superscript nx equal to integral 0 to pi by 2 kxt phi superscript n minus 1 t dt, where n varies from 1, 2, 3, etc., as given by equation 3.25. So that putting n equal to 1, we obtain phi superscript 1x as integral 0 to 1 kxt phi superscript naught t dt. Here phi superscript naught t is equal to 1, so that phi superscript 1 t is equal to integral 0 to 1 kxt dt. So that it becomes 0 to 1 e to the power x minus t dt for kxt equal to x minus e to the power x minus t. After simplification, this gives the value e to the power x into 1 minus e to the power minus 1. In similar manner, we obtain phi superscript 2x as e to the power x into integral 0 to 1 e to the power minus t phi superscript 1 t dt. Substituting the value of phi superscript 1 t dt, we get the value of phi superscript 2 x after simplification given by e to the power x into 1 minus e inverse. That is, it has the same value as phi superscript 1 x. So if I continue in a similar way, we get phi superscript 3x is equal to e to the power x into 1 minus e inverse, and finally phi superscript nx has the same value e to the power x 1 minus e inverse for n running from 1 to etc. Thus, the Neumann series solution of the given integral equation is phi x equal to summation n equal to 0 to infinity lambda to the power n into phi superscript nx, and if I substitute the value of phi superscript nx here, then phi x becomes equal to 1 plus lambda e to the power x into 1 minus e inverse into summation n equal to 0 to infinity lambda to the power n. Now this summation n equal to 0 to infinity lambda to the power n converges to the value 1 by 1 minus lambda for mod lambda less than 1, so that phi x becomes equal to 1 plus lambda e to the power x into 1 minus e inverse divided by 1 minus lambda, which can be further simplified to obtain the solution of the given integral equation as phi x equal to 1 plus lambda e to the power x minus 1 into e minus 1 divided by 1 minus lambda, and this solution is valid for mod lambda equal to 1. In this module, we have illustrated the method of successive approximations through some examples, and we have seen that the restriction on lambda in the method of successive approximation is just a sufficient condition.